Okay.
It's about the light stream. Let's just a minute. Great.
Okay, so you ready?
So yeah, now we start with your lecture.
Okay, great. Okay, hi everybody. Now this is the second lecture, and hold on, let me try the full screen. How's that? Does that work?
Yes.
Yes. Okay. The title is Scattering a Neutrino Alley, and today, actually, I'm still not going to get to that. I'm still kind of preparing to talk about Neutrino Alley. And so where we are in the 3 lectures, this is the second one where I'm going to talk, I'm getting a little more specific. I'm going to talk about physics with neutrinos in the few to 100 MeV range, and I'm specifically actually going to talk about solar and supernova neutrinos. And then I'm going to talk about physics with stopped pion neutrinos, so kind of artificial neutrinos in that same energy range. And so I'm going to mostly talk about these. And then the last lecture tomorrow will be more about actual stopped pion, a particular stopped pion neutrino source. And so just to remind you what we did yesterday, we talked generally about neutrino sources and about neutrino interactions and how to calculate event rates and neutrino detection, and generally how to important particle energy loss processes and techniques used for neutrinos. And so we're going to start to look at some particular applications of neutrino detection techniques for seeing neutrinos in the few tens of MeV range. And so this is the kinds of sources that exist in this range. And here is the same plot I showed with the spectrum over many orders of magnitude of flux and energy. And we're specifically going to look at 2 kinds of natural sources. There are solar neutrinos, which go up to about 15 MeV. And actually, I'm not going to talk so much about DSMB, which is the diffuse ones, but you can ask me questions if you have them. And then supernova neutrinos, which are burst neutrinos from core collapse supernovae. So let me start with the solar neutrinos. So the sun shines and we see the photons from the sun. That's our main energy source for life on Earth. And the neutrinos from the sun, or the photons from the sun, are produced in this chain, this web of nuclear reactions. There's a whole bunch of them. This is a big one here, which produces neutrinos. These are, and then there's some other different branches of this tree that also create neutrinos. These are all electron neutrinos that come from different processes in the sun, and they are named by these names. This PP is a big reaction that produces most of the neutrinos, and it's basically protons getting squished together, make electron neutrinos. This beryllium-7 and boron-8 produce higher energy neutrinos that we can observe. And it's all pretty much electron flavor neutrinos that are generated by the processes. And the spectrum is quite well understood from weak physics, from our understanding of weak physics. And so here's the famous picture of the energy spectrum of solar neutrinos that is predicted from our knowledge of nuclear fusion processes. And so you can see this is many orders of magnitude. It's a log scale on both X and Y. And this here, you can see this kind of shelf. These are the so-called PP neutrinos, which is a huge, vast majority of them. You can see on the log scale, it's dominating, but they are all very low energy. They are less than about 1 MeV. So these are very low energy neutrinos. Another one is this spectral line. So it comes out of a 2-body decay. So when you have a 2-body decay or 2-body final state, I guess not a decay, but a 2-body final state, you get a sharp monochromatic, that's this one right here, monochromatic neutrino. And so here it's at a bit less than 1 MeV here, this beryllium-7. You can see there's a couple of others of lower energy or lower flux, and one of them is lower energy. And then there's this spectrum here, which is a boron, so-called boron-8 neutrinos, which come from this process here. It's a 3-body final state, so it's a range of energies, and it goes up to about 15 MeV. And the flux is a lot lower. I mean, you can see here these boron-8 neutrinos are much, much lower flux than these PPs, but they're much higher energy, and that makes them much easier to detect. And in fact, those are most of the solar neutrinos that we see on Earth are actually from this spectrum, from this high energy and relatively high flux compared to these ones. Okay, so first poll. What fraction of the sun's produced energy so the energy, total fusion energy that gets released by the sun, what fraction of that, just you can guess if you don't know, what fraction goes into neutrinos? Is it 0.001%, 0.1%, 3%, 30%, 60%, or 99%? And so let's see, maybe I don't know if I can set up the poll myself. Okay, so here it is. Poll number 1. Okay, so I'm going to launch the poll. And so try to see if you can guess an answer. Well, this is an interesting set of answers. Okay, 10 more seconds. I'll close it. Okay, and the poll. Here are the results. Okay, so it's kind of a uniform distribution of guesses, except for the very lowest answer. And so the actually closest answer is 3%. It's actually about 3% of the total energy of the sun is released in the form of neutrinos. So that's maybe a fun fact. So it's not a majority, but it's kind of a non-negligible amount of energy that is escaping from the sun in the form of neutrinos. Okay. All right, so how do you detect them? So this is one of the earliest attempts, and maybe the earliest attempt by Ray Davis, who eventually got the Nobel Prize for doing this. And he started his experiment in the 1960s. And this is like one of those kind of experiments where, you know, if you do the back of the envelope calculation and think, is this experiment feasible? You think, oh my God, no way. How could you ever do that? That's really hard. And it's kind of like LIGO, those experiments, you think, my God, that's crazy. How could you ever try to do that? But in fact, it worked. He used a chlorine compound in cleaning fluid, and he looked for the charged current conversion of the electron neutrinos from the sun, absorption with chlorine atoms in this cleaning fluid to create argon. And then the argon was actually extracted macroscopically. So it was basically a handful of atoms every few months that were extracted, and then their decay was counted, which was a 35-day half-life. And so there was only 12 of these atoms. So you're thinking 600 tons of cleaning fluid, he was able to extract 12 counts per month. And so that's just a mind-boggling, crazy experiment, but he did it. And what he found was that there were not enough solar neutrinos. And that was for decades. That was since the 1960s. It was called the solar neutrino problem, because the calculation for how many solar neutrinos there were supposed to be was about a factor of, I think, 3 or so higher than, or maybe 2 to 3 higher than the expectation, or than the actual measurement. The expectation was higher than the measurement. There were missing solar neutrinos. And this was the solar neutrino puzzle that was for many, many years. And in fact, there was a science fiction novel by Arthur C. Clarke where the idea was that we found out that because it actually takes the photons about 1 million years to get out from the center of the sun, fusion is happening in the very center. And the idea was that the fusion had stopped in the center of the sun, and we wouldn't know that for 1 million years. And so humanity found out that, oh my God, the sun is going to go out, because it found that the neutrinos had turned, the neutrinos which get out right away indicated that the sun had turned off. But that was a science fiction novel. As far as we know, the sun has not turned off, as we'll see. Okay, and so then the next thing, so I'm going to do kind of historical overview of solar neutrinos. The next thing was a real-time directional measurement of solar neutrinos, and this was done in water Cherenkov. And as we talked about yesterday, when you have a charged particle going faster than the speed of light in water, you get a Cherenkov radiation, which is directional. It has a cone that is along the direction of the charged particle motion. And so what this experiment was able to do, the first one was the first Kamiokanda experiment in Japan, was able to observe the elastic scattering of electron neutrinos with atomic electrons and was able to use that directionality to actually point back to the sun, basically say, hey, we know these are neutrinos because they are coming from the sun. And so here's the picture of the original Kamiokande. This was 2 kilotons in Japan, actually the same mine that Super K is in now. It was actually originally motivated not for neutrinos, but to look for proton decay, actually. That's a side story. And this is their distribution. This is the number of events as a function of direction with respect to the sun. And you can see that the neutrinos are actually in an excess kicked away from the sun. And that is that's really a smoking gun, that the events are really neutrinos from the sun. And these are all fairly high energy neutrinos. So these are sensitive to the tail of the spectrum. These are really, if the threshold is 7 MeV, that's about here. This is only seeing this part of the spectrum here. And then Kamiokande turned into Super Kamiokande, which was able to do even better job, just do a much huger detector, 22.5 kilotons and a lower threshold. And here, in fact, Super K is still measuring solar neutrinos, and it's very clear they are coming from the sun. Okay, so and here's a picture. This is a kind of famous picture also. It's an image of the sun made in neutrinos, and this is a picture of the whole sky, the sun in the sky. And so I have here another question here. Here's another poll. And so maybe I can do the next poll. What said stop sharing? Okay, so that was already there. So I guess that was sitting on the thing. Sorry about that. Let me do the next one, pixelated sun. Okay, so here's the question. How many pixels does the visible sun occupy on this image? So you can see one pixel is like one box here. And so if you actually take the real sun and you were if you had this picture superimposed on the sky, how many pixels would the visible sun occupy? Is it less than 1? Is it about 1 pixel? Is it 10 pixels? So something like this, maybe this whiter area, 25 pixels or 60 pixels. So I will launch that. And so see if you can guess the real sun, how many pixels does the real sun occupy? Okay. All right, let me end the poll. Share the results. Okay. So the answer actually turns out to be, and so people are pretty close. The answer is actually less than 1. It's actually less than 1 pixel. So the people who said 1 are not too far off, and so that was the maximum answer. And in fact, it's really neutrinos are generated even in a smaller radius. In fact, this is a picture of where in the core of the sun the neutrinos are generated. And this is the fraction of the sun's radius. And so in fact, most of the neutrinos, if you actually look at the sun with your eyes, most of the neutrinos are actually generated within about a radius of 5% of the total radius of the sun. And so it's in a really tiny region that the neutrinos are generated. And because of the scattering of the electrons, which are scattered about 30 degrees or more, if you actually had neutrino eyes and you were looking at the sun would be terrifying. It would be enormous. It would take up an enormous part of the sky. So it's really only a tiny, the actual true source of the neutrino is really only a tiny area within the neutrino image. Okay. Get rid of this. Okay. All right. Okay, and so there's one other historical solar neutrino experiment, which is of interest, and this is another radiochemical experiment, meaning that it's another experiment that sits there with some material, and after the neutrinos have interacted, the material is basically scanned through to find the actual daughter atoms from a neutrino interaction, and then those atoms are counted. And in this case, the material was gallium. So this is not real time, and basically you have to integrate a lot of interactions, and then you, after the fact, count them. So you get kind of very large time chunks of data. And in this case, it was gallium goes to germanium, and the germanium atoms were detected, or extracted and detected. This interaction has a very low threshold. It's about 2.23 MeV, and the resulting daughter atom has a 11-day half-life. And so this is sensitive. So here's this plot again. Here are these very high flux but low energy pp neutrinos, and the threshold for gallium is such that it actually is sensitive to that flux. And so this is a measure of the very lowest energy part. This was a particular experiment was at using gallium chloride was at Gran Sasso and in Italy. And there's also a liquid gallium experiment in Russia. This one was called SAGE. In fact, this one, there's some sort of super crazy story where the gallium was stolen by gangsters, and somehow the director of the laboratory managed to get it back. But that's a different story. But both of these experiments were able to measure the neutrino flux from the sun. And in both cases, in all of these cases so far, it was a suppression. So there were fewer neutrinos seen from the sun than expected from the calculation. And so the hypothesis for that was that the neutrinos are oscillating. I think you've heard about neutrino oscillations. So the electron flavor neutrinos are basically turning into a state with a non-electron flavor amplitude. And so the measurement gives you fewer electron neutrinos than were generated. And so that was maybe the first signal of neutrino oscillation. And so there was that hypothesis was out there as a solution to the solar neutrino problem. But it wasn't really until the early 2000s that we knew the answer to the question, how do we know the neutrinos are oscillating? And that really definitive answer, which resulted in a Nobel Prize also, was the Sudbury Neutrino Observatory, which used heavy water, which has sensitivity to actually both charged and neutral current interactions of neutrinos on deuterium. So there's a charged current interaction, which makes a lepton. It basically breaks up the deuterium, which is a proton and a neutron, and it breaks that up. It turns one of the protons into a neutron and breaks it up and also makes an electron. And then there's also, and this is an important thing, there's a neutral current interaction on deuterium, which is also a breakup. It just breaks it apart. And also elastic scattering on electrons as well. And in this case, the Cherenkov light from this electron makes this interaction visible. And then there's, in addition, detectors that are sensitive to the neutron that comes out of the breakout. And this interaction doesn't care about the flavor. And so you can test if solar neutrinos are oscillating, because you'll get the expected rate of neutral current events, but the charge current events of electron neutrinos will be lower. And so that's the hypothesis they were testing. They had different mechanisms. We talked about how to detect how neutrons interact. And so they capture is one way you can measure them. So a neutron will capture on a deuteron, and you'll get a bunch of gamma rays adding up to 6.25 MeV. The heavy water was also doped with salt, with chlorine, which also captures neutrons, and you get an 8 MeVs of gammas. And it also can capture on special detectors of helium. And so Snow used all of these methods to see the neutral current interaction. And what they saw was that indeed, so this is a picture of their data, and they saw all of these three components. They saw the charge current events, which I guess are the pink ones here. There were the elastic scattering events, and those point back to the sun. And then there were the neutral current events, which are, I guess on this plot, are the dark one. And these also they have an isotropic direction. And all of these contributions were fit to determine the total flux to the sun. So this is a plot here showing the electron flavor flux inferred from interactions that are sensitive to charge current, and the non-electron flavor flux inferred from the neutral currents. And together, these say that, in fact, the total flux was consistent with the expectation from the sun. Here's the total flux, and the expectation is within these lines here. And in fact, this was really very clean evidence that, in fact, the total flux is correct from the sun. The sun hasn't gone out. It's actually fusing as we expect in its center. And the reason that we saw too few neutrinos, electron neutrinos from the sun, was that those electron neutrinos are have oscillated by the time we get to Earth. Okay, so there's one more major solar neutrino experiment. And this one is a scintillator experiment, a large liquid scintillator called Borgsino. It's a Gran Sasso, 300 tons, and very clean, very low threshold for a large detector, and also a real-time detector. So scintillation light is fast, so you can actually see the neutrinos as they come in, unlike the case of a radiochemical detector where you have to wait for a while and then extract. So you only get very big time bins. This is a real-time detector, like actually Super K is as well. And here the idea was to look for this sharp line from the beryllium-7 reaction in the sun, so monochromatic solar neutrinos. And what you expect there is a recoil spectrum. So the for scattering on electrons. So the neutrino comes in, it smashes an electron, it kicks the electron, you measure the scintillation light from the electron, but the neutrino takes away some of the energy. So you don't get all the energy of the neutrino in the detector. And this is the kind of spectrum that you expect here for beryllium-7 neutrinos. So with a maximum energy it can't be more than the neutrino energy. And this experiment has even measured these other interactions. In fact, has recently measured in fact, I don't think I have it here. It's actually recently measured the PP neutrinos. So it's really very low threshold, real-time detector. And the backgrounds here, you can see that the neutrino components of the signal are dwarfed by backgrounds. A lot of these other things are radiologicals. And so that can, this is really the game in this low energy measurements, is trying to reduce the backgrounds. And there's a huge effort to try to identify and reduce the backgrounds. And I guess you've talked about oscillations, but just I won't go into all the details of this kind of analysis, but I just want to mention there are also measurements. There are measurements of oscillation parameters. So the wavelength of the oscillation, which depends on the squared mass difference. I haven't talked about that, but I think you've heard about it. And the amplitude of the oscillation is determined by the so-called mixing angle. And from solar neutrinos, you can measure this by looking at how much disappearance you have. And you can also test this with reactor neutrinos at baselines of hundreds of kilometers. In fact, the Cameland experiment is what has done that. And I can point out there's actually currently in the world data a little bit of tension. It's sort of consistent, at the 2 sigma level, but it's a little bit of tension. So there might be something going on there. Now I want to mention DUNE, which is also possible. It's also a possible way of measuring neutrinos from the sun, low energy neutrinos. This, I think you've heard about this from Elena and other things. This is a big experiment in the US, lots of international collaborators, and it's a beam. The main purpose of this is GeV neutrinos with a long baseline to measure oscillation parameters, actually a bigger delta M squared and a different mixing, and looking for CP violation and delta M squared and mass ordering. But it's also sensitive to low energy neutrinos as well, coming from astrophysical sources in the sun and other places. And so that's also an important feature of DUNE. So here's pictures of DUNE. I know you've seen some of this. It's really very exquisitely precise tracking. There's different technologies under consideration and prototypes at CERN, and there's a lot of very exciting work going on here. And I just want to mention here that it's possible to measure solar neutrinos with DUNE. In fact, this is another very interesting application of this kind of technology. And here what you're doing is looking at this new ECC, basically charge current interaction of an electron neutrino from the sun with an argon that creates an electron. So you've got a nice track from a lepton, and it makes a final state nucleus, a potassium, that is excited. And then that nucleus then de-excites and it makes gamma rays. And so here's an example. So this is just a visualization of a simulation called Marley, which simulates a single neutrino interaction. So it will simulate the electron there's electron in I guess it's blue, and then you can see there's neutrons that are possibly ejected from the nucleus as it de-excites, and also gamma rays. Those are the red ones. And this is actually an event display of a 14 MeV neutrino coming from the sun, and you can see a little track. And these tend to be little scrappy events. But here's the electron, and then there's these gammas, and you get a really quite large number of these over the course of many years. And this is the example of the kind of spectrum you would expect. And you can see there's a lot of background here. You get this yellow is radon. There's neutrons that capture that also mess you up, but you have there's still a reasonable amount of signal there. This is coming from the boron 8 neutrinos. And actually this is the HEP neutrinos, which have not been observed so far and give you a very low flux, but high energy tail. So here's a question. So in this picture here, this event display of a charged current neutrino interaction in argon, and there's arrows there pointing to the de-excitation gammas. Now, based on what we did last lecture yesterday, what do you think those little blips are where the de-excitation gamma label is? Are they photoelectrons? Are they Compton scatters? Are they pair production? Or are they sparkles? In fact, of course, they may be sparkles. Let's go here. Okay, let me launch this. So what do you think they are? Okay. All right, let me end here and share the results. Okay. So that is interesting. Okay, so the best answer here is actually Compton scatters, that most of those blips are likely from Compton scatters. There could be some contribution from produced E plus E minus pairs, but in fact, that energy of the gammas is probably not high enough to make very many of them. They're probably mostly Compton scatters. There could be photoelectrons, that is true, but those are probably going to be mostly too low energy to see much. So the dominant is actually going to be Compton scatters. And the person who said sparkles, I think you are actually strictly correct also. I think they are also sparkles. Okay. All right, let me go on. Okay, so now I'm going to talk about, actually, this is one of my favorite things. This is another kind of neutrino signal that you would expect at the few tens of MeV range, a little bit higher than solar neutrinos, but more rare. So when you have a star that runs out of nuclear fuel, so when a star burns, it burns successively heavier elements. It starts by burning hydrogen into helium, and then helium gets converted into heavier elements, and you end up with a kind of onion skin of successively heavier elements until you get to iron. This is a simplified picture, but this is sort of roughly what happens. Is iron, you can't add more stuff to it and get energy out. And so iron is kind of like ash. It's at the end of the burning. And when you start to make iron, that builds up in the core of a star until there's not enough energy from radiation to hold up the star from the pull of gravity, and eventually the core will collapse, and it will squish down until it gets so dense that it bounces back, and it can create a supernova, and sometimes a black hole as well. But the result will be either a neutron star or a black hole. And actually, if it makes a black hole, it doesn't usually make a bright supernova. And that energy, that binding energy of the protoneutron star, turns into neutrinos of all flavors with tens of MeV energy. And it's actually mostly neutrino antineutrino pairs. And this happens over about 10 seconds. And it happens immediately after core collapse. And so here's a question. You can also guess the answer. What fraction of the binding energy is released in the form of neutrinos? From the sun, it was 3% of the energy of fusion is in neutrinos. When it's a core collapse, how much of that energy escapes in the form of neutrinos? So let me hold that one. Okay, so try that one. Okay, so let's see. Okay, so interesting. So in fact, the answer here is maybe surprising, maybe shocking. It's actually 99%. It is actually almost all of that binding energy of the resulting protoneutron star is released in the form of neutrinos. So it's a much higher fraction than for solar neutrinos. And the physical reason for that, so here's kind of a physical argument, is just as you have gravitational potential energy that turns into kinetic energy, thermal energy, if you drop something, that gravitational potential energy turns into other, sound, heat, that kind of stuff. It's the same thing when a star falls, that energy has got to go somewhere. Falls with a bang, and the energy that has to go somewhere, it escapes via neutrinos because it can. It's basically because of the weakness of the neutrino interaction. Because if you are a photon, you might get created, but you can't escape because photons interact with matter. And so, it takes 1,000,000 years for photons to get from the center of the sun to the surface of the sun. You can imagine in a supernova, it's a very hot, dense mess. If you're a photon, you can't get out, you're trapped. And so energy that goes into neutrinos leaves the star. And so all of the energy of the star will escape via neutrinos because it can. That's how it gets out. And it turns out it's something like 99% of that energy goes into neutrinos, and that all happens within about 10 seconds in the form of neutrinos and antineutrinos of basically all flavors. And that's kind of astounding. It's really enormous fluxes of neutrinos. And that's mind-boggling. It's actually about 99% of the energy. That 1% that's left, about most of that is actually kinetic energy of the expanding remnant. And then 1% of that, so basically 10 to the minus 4 of the neutrino energy is in photons. And these are, supernovae are enormously bright. They're as bright as a galaxy for a period of time. And so you can imagine the enormousness of the neutrino flux that comes out. And in fact, it's so much flux, it probably is involved in the explosion, although most of the neutrinos do escape. Some of them also deposit energy as they leave, and that energy is likely part of how the explosion happens. And this is something where there's a huge subfield of effort to try to understand exactly how this explosion happens. For a long time, the simulations didn't explode very well. Now I think the theorists are better at getting the explosions to happen, but it's still, a lot of things are not understood about it, and the neutrinos are very important in the process. And so we want to understand the properties of neutrinos, and we want to see the neutrinos from the neutrino burst because it will tell us about what is going on inside these stars. Now, unfortunately, these are fantastic events, but in our local neighborhood, a core collapse will only happen about a few times per century. And so they're rare events. And of course, that makes some people think, oh, I'm not going to bother waiting for that. But on the other hand, I think it means that we better be ready to get all the information we can if a supernova actually happens in our galaxy. And so here's a picture of our local neighborhood. Here's where we are in the Milky Way. Here's a nearby galaxy, Andromeda. And this is basically a radius over which we get about a few core collapses every century in the Milky Way and some of the nearby small galaxies. And so there's enormous information in these neutrinos, this 10-second burst of neutrinos. There's huge information in the distribution of the flavors and the energies and the time. And so here's a picture of an example model showing some of the features. Is what you get when the core starts to fall in is you start to get electron neutrinos. So here, the top plots are luminosity, so energy per time as a function of time. The bottom plots are average energy of the neutrinos. The different lines are the different flavors. So there's electron neutrinos, there's electron antineutrinos, and then there's mu's and tau's and their antineutrinos. And so this solid line is the electron neutrinos. And so you see them start to turn on. And that is actually, this is called de-leptonization or neutronization. So this is when you get protons and electrons that are squished together to make neutrons. So this is how you make a neutron star, is you actually have so much pressure that the protons and the electrons have a weak interaction and turn into neutrons. So that's another kind of inverse beta decay, I guess, in some way. And that releases an electron neutrino. And so you get this early flash of electron neutrinos, and you can see there's this spike here. There's actually a dip here. This is when neutrinos actually get trapped. And then you get a big spike called the neutronization burst in the electron neutrinos. The other flavors turn on. These are made in thermal processes. Then this time scale here is up to, so this is up to 50 milliseconds here. This time scale is about 1 second. And then there's about 10 seconds of cooling. You get sometimes interesting things happening having to do with the explosion in the middle phase. And then you get them all decreasing over about 10 seconds in the late stage. And you can see there's a feature here. These are the energies that the electron neutrinos are the coolest. They have the lowest average energy. The dashed line is the electron antineutrinos. They're a little bit hotter. And then the other flavors, the mus and taus, are hotter still. And I just wanted to walk you through here. And this, I don't have polls for this, but maybe you can answer in the chat. So somebody please try to, a few of you please try to answer the questions. So the question is, so this is kind of the physics, overview physics of what's going on in here. What is this reason for why is it that you have cool electron neutrinos, medium electron antineutrinos, and then hot other flavors? So here's the first hint. So to answer this big question, here's the first hint is, what kind of interactions does each flavor have with the medium at, say, a few tens of MeV energy? So, okay, here's answers in the chat. Let's see. Oh, a question. Which interactions are non-electron neutrinos coming from? So they're coming from cooling interactions, so they're neutral current interactions. In fact, I don't want to go to the next slide because I'll give you away the answer, but I can come back to it later. Is there's it's basically you can get for instance, annihilation of a quark and an antiquark, or a lepton and anti-lepton into a Z boson, and then it's a neutral current interaction, and you get a nu and a nu bar pair out. And so it's that most of the neutrinos come from these kind of processes. There's also things like plasmon decay, nucleon-Bremsstrahlung. So there's a bunch of processes that will give you pairs of neutrinos and antineutrinos in a neutral current from neutral currents. And so the neutral currents don't care about the flavor. And so they will give you all flavors equally. And so that's actually why you get all flavors equally. Okay, so question, I think the ones with electron flavor have both NC and CC, but the muon and tau types just have one of these. Yes, correct. Good, that's right. Okay, and so the next one, oops. Okay, yeah, so this was just a reminder of these different types of neutrinos. And so here, this is the answer here, is that we have charge interaction for electron neutrinos interact with neutrons, and electron antineutrinos interact with protons, and both of those nucleons are in a big soup. So they will give you charge current interactions. So this is all stuff is going on like crazy in this hot proto-neutron star. The nu X's only have neutral current interactions at these energies because they can't interact by a charge current. They can't make muons. So actually you'll get a little bit of it, but it's very much suppressed. Okay, hint number 2. This one is an easy question. Not a trick question, easy question. What is the proto-neutron star made of? Very easy. Somebody please answer in the chat. And I'm not trying to trick you. It's a proto-neutron star. What's it made of? Somebody must know the answer. Nope. Nope, not helium. Well, there's probably a bit of helium, but what is it? It's a proto-neutron star. Think about the name of it. What is a neutron star? Protons and neutrons, but mostly, which has more? What's it mostly made of? It's a neutron star. Neutrons, yes, neutrons, yes, it's a neutron star. So the answer is it's made of neutrons, mostly. I mean, it's absolutely true. There's other stuff. There's going to be a little bit of protons. There's going to be other nuclei. In the outlying matter, there's going to be all kinds of stuff. But in the inner core, it's going to be mostly neutrons. And so what does that mean? Okay, so given these answers to these questions, which flavors have more interactions? Here we've got the interactions that you have. You've got interactions on neutrons for electron neutrinos, interactions on protons for electrons and antineutrinos. You've got mostly neutrons hanging around. So which flavors have the most interactions? Yeah, exactly. Electron flavor has the most interactions with material because it also has neutral current interactions, but it has charge current interactions, and there's lots of neutrons around to have charge current interactions with. And so electron neutrinos has the most. After that, you've got nu bar, since all of them have neutral current, and nu X, the mus and taus, have the fewest. Okay, so you have different amounts of interactions with the protoneutron star with different flavors. Okay, now let me give you another terminology to answer the overall question. So a neutrino sphere is defined as the surface at which the neutrino mean free path is infinity. So you have a very dense material, and neutrinos are actually interacting a lot. It's so dense, even neutrinos are interacting a lot, but you have a surface at which the density is low enough that neutrinos are basically going to stream to infinity. And that's called the neutrino sphere. That's just defined as the distance, where the density gets low enough that the neutrinos can escape. So where are the neutrino spheres for each flavor? So there's a neutrino sphere for electron neutrinos, which has a certain amount of interactions, then one for electron antineutrinos, and then one for new mu's and new taus. So which neutrino sphere, which is the smallest radius neutrino sphere? And which is the highest radius neutrino sphere? So if you have a lot of interactions, is the neutrino sphere bigger or smaller? I think you've got it backwards. If you have a lot of interactions, if you have a lot of interactions, your neutrino sphere is farther out. Okay, then it takes you, it's harder if you're bumping into lots of stuff, it takes you, you have to stream out farther to decouple. And so the largest neutrino, you have a larger neutrino sphere when you have a lot of interactions. And so the largest neutrino sphere is for the electron neutrinos. The smallest neutrino sphere is for the other flavors, the mu's and taus. Okay, then, so the last question is, how does the temperature vary with radius? If you have a very hot, dense thing, do you think it's hotter towards the center or cooler towards the center? If you're deep inside, do you think it's hotter or cooler? Hotter in the center. Yeah, so you're hotter in the center. And so the deeper you are, the higher the temperature. And so we can put this all together. If you are decoupling from very deep inside, then you are decoupling with a hotter temperature. And so you have this neutrino sphere that is deeper. So for muon and taus, you're decoupling from the star, you're leaving the star, you're streaming away from a place where it's hotter, where your average energy is higher, and that gives you a higher average energy. And so that means that the muon and tau, neutrinos and antineutrinos, are coming out from where it's hotter, and so they are coming out with higher average energies. Yeah, so the answer is yes, it goes pretty much, yes, as the inverse of the neutrino sphere radius. Yes, the shorter the mean free path, the higher the radius. And so this is a kind of the basic idea. This is not completely robust for the entire time scale. There's actually things that mess it up a bit. Neutrinos can change their flavor, as you know, and that modifies things. But this is kind of a general property that the mu's and taus are hotter than the Nui bars, and the Nuis are the coolest. Okay, and here's a picture. This is what the spectrum looks like. It's a kind of modified thermal spectrum. It's sort of Fermi-Dirac-ish within some modifications. And it has this sort of general property that you've got these slightly hotter new X's compared to the new E's, which are the coolest, and then in between the Nui bars. And so this is just an analytic expression that describes it. This is just a visualization of it. This is a two-dimensional visualization. So these three columns are time scales. So these three are 50 milliseconds. This is about 1 second or half a second, I guess. This is 10 seconds. These are the Nui flavors. These are the Nui bar flavors. These are the new X flavors. This is energy on this y-axis for all of these. And so this is kind of showing you, and the intensity of the color is how many of them you have. And so this is showing you how the energies change with time. So for the Nuis, you have this is the neutronization burst. You get this bright flash in very early times from the protons and electrons getting squished together, making electron neutrinos. And then here you can see the cooling. And this is, so there's kind of less features in the Nui bar and the new X's. And there's also a really interesting thing you could see. If a black hole forms, what you get after about 2 seconds is you get a sharp cutoff. So basically what will happen is bam, when the black hole forms, nothing can escape, the neutrinos can no longer escape. And so you will see a very sharp cutoff of the neutrino flux. And so that would be something that would be really, really exciting to see if we could actually observe the neutrino bright burst and then bam, nothing. You would actually see the black hole being born inside the supernova. So that would be really, really amazing thing to see. And in fact, in that case, you might not get a really bright supernova or any supernova at all. Okay, let me just briefly mention, we actually have observed this once, probably before you were born. It was not before I was born, but I do remember when it happened. It was before I was studying neutrinos, but this is the 1987A supernova in the Large Magellanic Cloud, which is a small galaxy outside our own galaxy. There were about 24 neutrinos that were seen from this in 2 different water detectors. And okay, here's just an informational poll. So what is a kiloparsec? I've been talking about kiloparsecs and parsecs and so on. It's a question from YouTube. Are people worried about undesirable excess in neutrino signal if when a supernova explodes and gets to Earth? Oh, so could it be dangerous for humans? The answer is probably not. You'd have to have a really, really, really close supernova for it to be dangerous. And in fact, Betelgeuse is very close. And if it goes off, it will be very bright and we'll get a huge neutrino signal. That one is about 180 parsecs away. And oops, I gave away something. But even that is probably not dangerous, although it's the kind of thing it would make excess cosmic rays, but they wouldn't actually arrive at Earth for maybe 100,000 years. So the effect could be, for the detectors. Is it basically so bright that it fills the buffers and crashes the detector? And so the answer is yes, people worry about that. Yes, and so people are worrying about being prepared. In fact, that's kind of the job of neutrino experimentalists. And most of the big collaborations have indeed prepared a lot for this. And it could be if you have a really close one, you could have so many signals that you crash your data acquisition, and that is a worry. And in fact, it is something that experimentalists do prepare for, make sure that the detector is not going to crash. Of course, the thing you worry about is, oh my God, the alarms are going off and then people turn off the power to try to fix it. That's something we've worried about in Super K. So there are precautions against that we definitely don't want to lose the data. It happens so rarely, that would be terrible. And so we really, definitely worry a lot about being prepared. Yes. Okay, so question here, a poll. Let me try to start this one. Stop this. And next one, so kiloparsecs, this is really just the definition. So what's a kiloparsec? Is it a unit of distance equal to about 3260 light years, a unit of time equal to about 3260 years, approximately the distance to Betelgeuse, or a leisurely amount of time to complete the Kessler run? So this is probably an easy question. Okay, let me end this, show the results. Okay, good. So most people got this right. This is a unit of distance. It's about 3260 light years. Betelgeuse is 180 parsecs away, so quite a bit less than a kiloparsec. If you chose the last one, you wouldn't be exactly wrong if you were in the Star Wars universe. The Millennium Falcon was able to complete the Kessler Run in 12 parsecs, so that'd be plenty of time. But that's in Star Wars universe. Parsec is not a unit of distance, it's a unit of time. Okay. Okay, and here are the neutrino events that came from 87A. There were 2 water Cherenkov detectors that were running. There was the Kamiokande 2 detector, which I showed you the solar neutrino results for. There was also one in the US called IMB. And they saw events that were pretty much consistent with what was expected. So about 10 seconds and a few tens of MeV neutrinos. They had fairly high thresholds, but this was really almost all Newey bars. So these are inverse beta decay events. And so they were almost all Newey bars, but that's because the detectors were only sensitive to Newey bars, not because the burst was only Newey bars. And so we really need more data. This is a very sparse sample, lots and lots of papers written about it, but we still need more information for the next one. And there are a whole bunch of detectors that are running now. Most of them are built for other purposes other than supernova, but they are nevertheless sensitive to supernova bursts. And there are different categories. I don't really have time in this lecture to really go through all of them in detail, but I'll tell you something about them. So there are water Cherenkov detectors like Super K, also long string detectors like IceCube. There's Dune, I'll say a bit about Argon. There's also large scintillator detectors. There's, I won't say too much about this, but there's one small dedicated lead-based detector in SNOLAB. And then also, and this is what I'll talk about maybe a bit more tomorrow, is there are dark matter detectors that are also sensitive to a burst from supernova and other kinds of detectors. So I'll say a little bit about water Cherenkov. So I've already talked about this. This is a where you get a cone of light from particles moving faster than the speed of light of water. And what you actually see is the positron that comes from inverse beta decay. So water has lots of free protons. It's H2O. We've got two H's. Those are the protons. This has a threshold of about 1.8 MeV. And you'll see mostly the positrons and also sometimes the neutron capture. You can also see elastic scatters. So electron neutrinos that, just like the solar neutrino signal, electron neutrinos that kick electrons and make a cone. And this is actually very valuable. It's actually a small fraction of the total, but it gives you pointing information. It actually tells you where the supernova is. And this is a picture of a map of the sky. This inverse beta decay is actually almost isotropic. It's basically the positron forgets where the neutrino came from, but to a decent approximation. But this elastic scatter, when you have a neutrino that kicks an electron, just like for the solar neutrinos, the electron remembers where it was kicked from, and so you get a bump on a background, and so you can use that to point back to where the supernova is. And that's actually important for astronomers, because if you tell an astronomer, hey, oh my God, a supernova happened, we saw the neutrinos, they're going to be irritated if you don't tell them where it is. So if you can actually tell them at least approximately where it is, that is a huge benefit. Okay, so here's a little simulation of Super K for a supernova burst. So this is the unrolled view of Super K. So each little dot is one photosensor. This big black part is the inner detector. And the outer detector is kind of the outer veto. And when I click on this, it's going to show you in quasi real time what a supernova burst would look like in Super K. So there you go. So that's mostly background, bam. So you would see all in 10 seconds, you would see a really huge number of events. The whole detector would light up. You can see some of them are rings, some of them are too small to be really distinctive rings, but it would be really a very bright show, and you could see where the neutrinos are coming from as well. And you build up the energy spectrum of observed. These are almost all inverse beta decay events, except for the ones that are pointing, which are elastic scatters. And there's another thing, this is something new. Oops, I see something in the chat. Let's see, question. Do we expect that when the supernova neutrinos arrive to Earth, the oscillations will make the flux of the three flavors the same? Great question. That is a huge question that I'm not going to get into the details of, but that is a really important and interesting thing. That in fact, yes, the oscillations matter a lot. In fact, they matter mostly in the supernova. That in fact, the distance to the supernova is long enough that the neutrinos don't oscillate much anymore, because the different flavor states have actually decohered. And so in fact, neutrinos propagate as mass states. But in fact, the oscillations or the transitions are really important in the supernova itself. And yes, that does mix up the flavors. And that's actually, that's a whole huge topic that I won't get into in this lecture, but that is a really interesting, that's how we can learn about what is going on with neutrino. In fact, we can probably learn about the mass ordering from what we see in the signal. There's also a whole regime, which I think is not really theoretically settled yet. There's a lot of theory work on it right now. It's called collective effects, and it's actually fascinating. The supernova matter, the protoneutron star matter, it's so dense that neutrinos actually interact with each other. So for a short period of time, you actually have neutrinos that are interacting with each other, which is crazy, because neutrinos are so weakly interacting that having them interact with each other is nuts. But it actually happens, and it causes some very complex and interesting behaviors that we might be able to observe by looking at the flavors and fluxes, flavors and energy as a function of time. So yeah, that is a great question and a kind of a whole subfield of interesting stuff. So yeah, thanks for that. And so really what we want to do as experimentalists is figure out how can we best measure the fluxes and flavors and energies as a function of time. Okay, and so here's actually a way in SuperK that we can do this, is that we can actually tell that an event is an electron antineutrino if we can see the coincidence. And this you've probably seen, this is inverse beta decay that's used for reactor neutrinos, for example. If you can see a time coincidence of the positron and the neutron, then you can tell that that event was an electron antineutrino to a good probability. And so you want to be able to see this neutron. And you can actually, in water detectors, you can actually, I call this drug-free because you do it without any kind of doping. You can tag that neutron by a capture on proton, which makes a gamma, and you can see the Compton scatters of those gammas, a little bit of Cherenkov radiation from it. And in a just pure water detector like SuperK, it's about 18% neutron tagging from this process, which is kind of low. But what is happening in SuperK now is we are adding gadolinium to the detector. Now, gadolinium is an isotope that is hungry for neutrons. It likes to gobble neutrons, and then it spits out a bunch of gamma rays after it's captured that neutron. And you can see the Compton scatters of those gamma rays. You can see about 4 MeV of energy when a gadolinium gobbles a neutron and then spits out gammas. And that is a much easier tag, so you can tell that you have Nu bars. And in fact, this is happening. SuperK is now in the process of being doped with gadolinium. In fact, the first gadolinium went in some time ago, and it's now running as so-called SKGD. So this is a new, exciting recent development, and will improve the ability to determine the different, basically tell what kind of interactions we have in SuperK. Okay, so this is another kind of water Cherenkov detector called long string, and there's several instances of it, and one prominent one is at the South Pole. This is the IceCube detector, which has got a bunch of photosensors that are dropped in the ice in very long, underneath the ice in very long chains. So it's like kilometer cubed scale kind of detector. The photo detectors have something like 10 meters in between them. And it's nominally trying to see not low energy neutrinos, but really high energy neutrinos. So PeV neutrinos, and it has succeeded in doing that. So basically seeing these enormous events. This is a picture of one of them. Very colorful, pretty events. And you think, well, those are, TeV, PeV neutrinos. How could you ever see MEV neutrinos? You only get photons around one phototube. But it turns out that IceCube can actually see a supernova by seeing the glow of Cherenkov photons in the ice during the 10-second burst. And actually, this is a very cool idea, and it seems like it will actually work, is what you see in all the photos. So the phototubes are constantly having single photon noise and being recorded all the time. And so there's kind of a background of photon noise. But during a supernova burst, what it will see is an increase in that noise. You'll basically see the whole ice glow over the course of 10 seconds, and it can use that glow to observe a supernova. And so that's it's probably sensitive. IceCube is sensitive to maybe the center of the galaxy, or in fact, I think IceCube, the whole galaxy. So that's actually very, very cool. Okay, so let me talk a little bit in the context of supernova neutrinos about scintillator detectors. And so scintillator, we've already talked a bit about it. It's liquid hydrocarbon. Large liquid scintillator is made of CnH2n approximately, and actually can get a lot of light out of it when a charged particle loses energy. This is also sensitive mostly to inverse beta decay, to electron antineutrinos in the same way. So the free protons are the H's, and you get Nu bar on H, and you get a positron. This is also used for reactor neutrinos, and a neutron, and also you can see the coincidence in the neutron. Usually you can see that very well because you get lots of photons, and so you use that double bang kind of signal to identify these events. There are actually lots of instances. We saw also Borexino, just in the context of solar neutrinos. There's CAMLAND in Japan. The SNO detector is now finished. It's now being filled. It's, I think, got scintillator in it now. It's also a kiloton of scintillator called SNO+. There's also detectors on the surface. This is the LVD detector in Italy, and there's a detector called Juno, which is under construction in China, 20 kiloton. And the last detector I'll talk about in detail for supernova neutrinos is argon. And you've already heard a lot about argon TPCs, which are fantastic detectors. And you heard about this for solar neutrinos. You get this charge current interaction where an electron neutrino hits an argon nucleus and you get an electron, which will show up as a little stub. It'll be a track and an excited state of potassium. So this is the same interaction as solar neutrinos. These are some existing detectors or under construction detectors, including DUNE, which is 40 kilotons. And a nice property of DUNE, this is a kind of a current study, is you can actually also use it for pointing. What you get when you get a scattering off an electron, you also get, everything has electrons. You can have a neutrino scatter with electrons. You get a little track like this. These are 3 different views from, this is a wire plane and 2 induction planes. Is you can actually see these tracks and use them to point back to the supernova. And unlike a Cherenkov detector where you get a ring which is going forward in the direction, if you just have a track, you don't know if it's going forward or backward. And so you have to use some tricks to tell the difference. And in fact, what some students, in fact, there's more students working on this now in DUNE, is to try to figure out how well you can point back to a supernova. And here's just an example. You can use a likelihood to figure out, okay, where's the direction on the sky that the supernova happened? And maybe just look at this one down here. This is the pointing to the supernova this is the angle with respect to the supernova. It actually points back very well if you use a sample of a whole bunch of elastic scatter events that come from a supernova. So this is another a cool thing that DUNE can do. Okay, so here's a table. You don't have to read all the entries. I just want to give you the impression that there's a whole bunch of detectors that are running today and that are under construction for the future, which have sensitivity to supernova neutrinos. So the ones in purple are the ones that have either recently stopped, actually Diabase, I probably should update that one, that actually stopped recently. But the other ones I think are still running. And these are ones that are running very soon. Snow Plus I think is running now. And these are the future ones. And so it's really a variety of different technologies here: scintillator, water, long string. These are the argon ones, and these are the numbers of events. So it ranges from typically a few hundred from scintillator detectors. Super K expects maybe 5,000 to 10,000 events. And so contrast this to about 25 events for 87A. So it's a huge improvement. And then very big detectors like Hyper K, actually, I think this number is smaller now. That was the original proposal, but it's going to be a very large number of events, tens of thousands of events. Juno, maybe 6,000. And then IceCube it's not events, but you get a nice timing signal. So it's really lots of current and future experiments are sensitive. And yes, there's been a lot of preparation to make sure that these are running. And are going to be able to swallow a supernova, because if a supernova happened and we didn't see it, it would be a disaster. Okay, so here's a question, just a scaling kind of question. So these estimates that I have in this table are for 10 kiloparsecs, which is just beyond the center of the galaxy. And so you can see approximately the scale of the number of events you would see. And so DUNE, you can see, expects about 3,000 events for 10 kiloparsecs. And so here's the question that you can do with a short calculation. So if you have a core collapse in Andromeda, so Andromeda is 70 kiloparsecs, and 700 kiloparsecs, so it's outside our galaxy. How many events would you expect in DUNE if a core collapse happens in Andromeda? So and you should be able to do a short scaling calculation to get that. So let me put the poll here. In Andromeda. Okay, so try that one. Okay, Okay, well, so the answer is actually probably something closer to about 1. There's a lot of variation in the models. It could be 10, but it's probably going to be closer to about 1. And let me show you the plot. Oops. Okay, so here's an example. So this is just 1 over distance squared. So you expect a scaling of the events with distance to the supernova of about 1 over distance squared. And so that's just what this plot is. And so this plot shows you for a particular model, and the models do vary quite a bit, probably by a factor of 10, how much you would expect. So this red line is for argon. And so here's the galaxy edge. And so you expect something like a few times 10 to the 3. This model looks like it's maybe something like 10 kiloparsecs is a few times 10 to the 3. If you go out to Andromeda, which is here, it's going to be something like 1. So that's basically not a huge number. For Hyper K, although Hyper K I guess is smaller now, you would actually get maybe a dozen events, something like that. So Andromeda is pretty far, and 1 over r squared is hard, but it would certainly still be very interesting to see a supernova in Andromeda. Okay, and so here's kind of a summary of what we would learn, and it's really enormous number of things. So you learn about the core collapse physics, because you can see inside, the neutrinos let you see inside what is happening. So you can tell what the explosion mechanism is. You can see the star cooling. You can see a black hole being formed. There's also other things. I won't go into the details of this, but there's all kinds of interesting accretion signatures of things that are happening inside the star. A strange star is formed that can give you a late burst. That's quark matter. And you can also learn about neutrino physics. You can learn about absolute mass, and somebody asked the very good question about mixing. You can learn about transitions from the flavors. There's other properties you might be able to learn. And also there's possibly exotic physics you could learn. There could be signatures for axions. There's signatures based on energy, that if other particles exist, then some of that energy would have to leak away in those other particles. And so the fact that you see a certain amount of neutrinos will limit how much extra energy can be going into other particles. And so there's a lot of possible implications for particle physics. And this is kind of a virtuous circle in that the more you learn from neutrino experiments on Earth, the better you can extract the astrophysics. And the more you learn about the supernova from a photon or other observations, the better you can extract neutrino physics. And so if we actually get one of these, it will be fantastic. And we also want to learn from gravitational waves as well. And let me just make a very brief mention of the early alert. And are we preparing? And the answer is yes, we are very much preparing for the next supernova. There's a network called SNOOS, Supernova Early Warning System, which is an international network of different experiments, and currently involves 7 experiments, although Diabé has recently completed. And so we don't have that one anymore, but we have more that are coming in. And we are actually in the middle of upgrading this to a more modern system with a better alert dissemination. And so, stay tuned for that. It has Super K, Camland, Borgsino, IceCube, Halos, a lead detector in Canada, and LVD. Okay, and so you were probably wondering, the title of these lectures was Scattering in Neutrino Alley, and I haven't really talked about that yet. And so you're probably wondering, what does all this stuff that I'm telling you have to do with that? And in fact, there are connections. And so let me tell you what that is. And we're going to get to that a bit more tomorrow. So we talked about inelastic interactions, and I didn't say so much about this in the context of supernova. Mostly I talked about inverse beta decay, but inelastic interactions with neutrinos and nuclei are important. Actually, the argon interaction is inelastic, and we actually don't have a very good understanding of these cross sections of these interactions. There's not that much theory. There's some theory out there, and there's almost no experimental information about it. There's actually the only measurements that exist at better than the 50% level are on carbon. There's some sort of 10% measurements on carbon. So there's almost no information experimentally out there about neutrino nucleus interactions. Oops, I see a question in the chat. Are people working on a way to estimate when a supernova will come? Okay, great idea, a great question. The answer is, that's very hard. That yes, there's a couple of ways to have a clue that a particular star will blow up. And one of those ways is from optical observations, that there are some astronomers, and this is actually a field, I don't know that much about this, but I believe there are ways of looking at the sort of unstable behavior of a possible progenitor star to get an idea that it might be about to blow up. And in fact, you may have heard about Betelgeuse. Last year, there was a Betelgeuse's luminosity was changing, and some people were saying, oh my God, it's about to blow up. It turns out that actually that sort of signature is not very, not really a good indicator that Betelgeuse might blow up. That's actually mostly having to do with the outer layers of the star. But there are possibly some signatures that a star is about to come to the end of its life from astronomy. There's actually another very interesting one having to do with neutrinos, is that there's what's called pre-supernova neutrinos. And these are neutrinos that are created from the fusion processes at the very end of the star's life. And so when it's burning things like silicon, it's burning heavy elements, you get more neutrino production and hotter neutrino production. And those are still very faint signals. They're actually, it's probably only observable in very nearby stars. Actually, Betelgeuse is one of them. And it's something actually that a number of us are working on in the community, of trying to find, to see if we get an excess of low energy neutrinos that is actually increasing with time over a few days or weeks, which could tell you that a supernova that a star is about to collapse. And so, for example, we might be able to see if Betelgeuse is about to blow up by seeing an increase in the neutrino output, actually seeing neutrinos from a nearby star. And that will probably only work with our current and near future detectors in a near radius, so maybe within a kiloparsec or so. But it's something very interesting that we are trying to set up. In fact, CamLand already has a pre-supernova alarm, which is probably only sensitive to maybe 5 or 10 nearby stars, but it's something that we are working on trying to improve. And we might be able to increase the radius of sensitivity out to maybe the center of the galaxy with next generation detectors. So yeah, that's actually a very exciting question. That would be a really, that's a next generation, a true early warning system. So yeah. Okay, all right, so we don't understand inelastic interactions all that well, and we need to understand them better. And here's just an example. This is a study. These are a bunch of different theoretical models of the cross-section for neutrinos interacting with argon, for charge current nu-e on argon, which is the interaction I showed you before. And this is a log scale. You can see that these different models, there's a big variation in them. And the difference between these models give you actually quite a big difference in what you would see in a detector. So this is just to give you an idea. And some of these models are better than other models. They're not all of equal quality, but even so, you can see that, there are going to be quite large uncertainties on what we're going to see. And so if you actually had a signal, it would make it hard to interpret what that signal means. And so we really need better information. And this brings me to pion decay neutrinos. So neutrinos from pion decay at rest, or stopped pions. So this is a kind of natural source of neutrinos, a kind of artificial source of neutrinos that is just in the right range to do a lot of really interesting studies. And so the way you can get this kind of artificial neutrino is you slam protons into a target with enough energy that you actually create some pions. These pions will then decay, and if you have a material which is dense, the pions that are created will stop and then decay at rest. And so a decay at rest, it's a two-body final state, and that means that each of the two bodies has a monochromatic energy based on how much energy is available for the decay. And so for pion decay, which is a two-body decay, you get a monochromatic nu-mu at almost exactly 30 MeV. And so that's what this is here. You get a single energy muon neutrino when a charged pion decays at rest. Then you get a muon, that's the other product, and that decays by a three-body decay. This is one that maybe some of you have measured in a lab. It has a decay time of 2.2 microseconds. And it has a well understood spectrum of neutrinos. You have new E's that go up to 50 MeV and also new mu bars that go up to 50 MeV for a positive muon. You get the charge conjugate if it's a negative muon. And so this is a well understood spectrum. This comes from basic weak physics. We know exactly what that spectrum is. We know what so we know the energies and we know the time scales. And so this is a very, very nice source. And it goes up to about 50 MeV, which is exactly where the supernova neutrinos are. The solar neutrinos are at kind of the lower end of it, but overlap. And so this is a perfect kind of source to study supernova neutrinos. And so if you can make them, so this is just a plot. This is also just showing the same spectrum here, just different colors. The SNS stands for spallation neutron source, which is an example source of such stopped pion neutrinos. And here what I've superimposed on it is an example supernova spectrum. And you can see there's really quite a nice area of overlap. And so if you have these stopped pion neutrinos, you get a very good handle, understanding of what, if you can measure, if you know what your flux is and you measure interaction rate, you can infer the cross section, and you can therefore learn what the cross sections are so that you can get flux information from measuring a supernova signal. And so, oops, okay, those are out of order. Okay, so, and this is how much you get. You need to get a reasonable flux. And so this is an example of the spallation neutron source, which I'm going to tell you much more about, and other sources tomorrow. So if you integrate in one day the fluence, so fluence is flux integrated over time. So it's basically neutrinos per area. In one day, if you integrate the fluence from the spallation neutron source, stopped pions, and plot this here as a function of distance. So this is just 1 over distance squared, 1 over r squared. This is the fluence. So this is the flux integrated over time from a supernova at the galactic center, approximately. You can see that they cross here at about, let's see, where is this? This is at about 50 meters. And so this is basically kind of like an artificial supernova. Every day, if you're sitting 50 meters from the SNS, it's kind of like, it's like getting 1 supernova's worth of neutrinos a day. And another way of saying that is if you've got 60 hertz of pulses, you get 0.2 microsupernovae per pulse. So it's kind of like having an artificial supernova that you can just sit in the flux of the neutrinos and make measurements with a well understood flux. And so having a nice source like this is a really great opportunity to understand neutrino nucleus interactions in the supernova energy range. And actually there's a lot more motivations, and I'm going to talk more about those next time. Okay, so actually go back to this. So this is now my summary for today. So solar neutrinos, these are neutrinos up to 15 MeV. There's a huge rate below 1 MeV where it's hard to get to. These are very interesting to measure still. Of course, historically very important in understanding neutrino oscillations. In June, there's interesting opportunities with new ECC. For supernova neutrinos, we've got all flavors, goes up to about 50 MeV, all in a 10-second burst. Very rich physics and astrophysics to be had, multiple detectors worldwide of different kinds. Inelastic neutrino interactions have a big uncertainty. So if we want to profit from these signals, and actually other ones, but I've focused on solar and supernova, we need to understand what the cross sections are. And that's where Neutrino Alley comes in, is that it's a place where we have stopped pion neutrino source, which is kind of synthetic supernova or synthetic sun, maybe even for neutrinos, maybe not quite the right flavor. But I'm going to talk more about this tomorrow and what we can learn from that. So that brings me to the end of today. And so what we will get to tomorrow is, I hope I've motivated at least part of the physics motivation for going to Neutrino Alley. And I will tell you more, and there's actually more stuff that's not related to supernova, more physics to be had there that I will tell you about as well tomorrow. So that's all. I will stop there. Happy to take more questions.
Thanks a lot, Kate. Do we have any questions? More questions, in fact. There's one.
Yep, lots of good questions.
Okay, just thanking for it for the beautiful talk. Okay. So thanks again, Kate. Very, very nice. And we're looking forward to tomorrow.
Okay, great. Looking forward to tomorrow, and I will see you then.
Okay. Bye-bye then.
Great. Bye.
Bye.